In this video, we're going to talk about exponential functions, and like quadratic functions in those videos, I'm just going to do a quick overview here and then some examples. So exponential functions in general are always in this form, f of x equals a times b to the x power. So notice that the variable x in this case is in the exponent position. That's different than like in a quadratic, for example, where the exponent was a number like x squared, it was 2. So there are some conditions though. So a and b are non-zero real numbers. So if we think about that for a second, if a or b were 0, it would be hard to have an exponential equation because watch what would happen. So let's say a was 0. So maybe we have 0 times 3 to the x power. Well, 0 times anything is just 0. So that really would just be f of x equals 0, which is really just a straight line. It's not exponential. And if we had b as 0, then we'd have f of x equals, let's say 3 times 0 to the x. Again, 0 to the power is anything, times 3 is just 0, so we would still have f of x equals 0. So that's why those conditions are there. We don't want those numbers to be 0. And then the other condition is b cannot be 1. So give you an example. So like if f of x was equal to 5 times 1 to the x power, well, 1 to any number, it doesn't matter what x is, 1 to any number is just 1, so it would just be 5 times 1, or f of x equals 5, and that is also a straight line, so it's not an exponential function. So examples of exponential functions. So I'm just going to, cross all of these up off top up here because those don't work. But examples of exponential functions might be f of x equals, 2 times 3 to the x power, or g of x equals, 5 times 0.3 to the x power. And if we graph these, so let's just go over, I'm just going to pull up Desmos real quick and we'll graph these. So this is desmos.com, and I'm just going to plug in y equals, and then we'll do 2 times 3 to the x power. So you have to press this a to the b power button and then put an x there, okay? And so if we look at this function, we've got this, curve here. It's really pretty flat near the x-axis, but then it jets up really, really high. So 2 times 3 to the x, we call this exponential growth. So let's go ahead and I'm going to write that in our notes. So this graph right here is exponential growth. It's kind of like the example that I just gave. So that's one option for what a graph could look like. And then notice in the second example, I purposely chose a number that was smaller than 1 because that represents decay. So I'm going to show you what that looks like. If I graph 5 times 0.3 to the x in Desmos, so I'm going to go over here and I'm just going to erase that. And I'm going to put 0.3, and then I could even leave it at 2. It really doesn't matter. But if we zoom out here, you can see now that going from the left to the right, we're sliding downward. And so this is exponential decay. And the reason why it's looking like this is because the number inside of the parentheses, or that base at the bottom of the exponent, is a smaller number. It's a number less than 1. Okay, so with our example here, this would be an example of exponential decay. And then this is just summary right here, growth versus decay. So the value of b, so remember I'll write the equation down, a times b to the x power. So the value of b in an exponential equation can tell us the rate of growth or decay. So if b is greater than 1, we have exponential growth. And then if b is less than 1, so like my 0.3 example, then we have exponential decay. And then if you want to actually find the growth rate, it's really easy. All you have to do is take that number, subtract 1, and multiply by 100. So say, for example, we had a function f of x equals 1.04 to the x power. B is greater than 1, so we know we've got exponential growth. If I wanted to know the growth rate, I would just do 1 minus 1.04, which is 0.04, then times 100, which is 4%. So that function would have a 4% growth rate. Okay, and the same is true with decay. You just take that b value, subtract it from 1, and multiply by 100. So how do we graph? We could spend a lot of time on graphing. I'm just going to give you some pointers, some quick pointers here. So if we're graphing on Connect Math, a really nice tip is to find the value of x that makes the exponent a 0. So for example, we're going to look at y equals 3 times x plus 2. We identify the exponent, so it's all of this stuff, and we say, when is x plus 2 equal to 0? Well, you could think about it. It's equal to 0 when x is negative 2, okay? You could also solve that equation. So x plus 2 equals 0. You could take away 2 from both sides, and you get x equals negative 2. So it's 0 when x equals negative 2, okay? So we find, its exponent is 0 when x is 2 or negative 2, and then we can just create a table of values when that happens. So let's see, we're going to make a table of values. So what I can do here is I can see that plugging in a negative 2 might be a good idea because that makes things easy. So if I plug in a negative 2, I get y equals 3 times negative 2 plus 2, which is 3 to the 0 power, and that equals 1. So it makes a nice number because when we're graphing on Connect Math, we kind of want to avoid decimals that need to be rounded because those are a little bit harder to graph. So at least this guarantees that we've got one whole number there. And then we can pick, a couple values nearby. We'll maybe pick 2. So maybe I pick one on either side of that. So maybe I pick x equals negative 3. So y equals 3 to the negative 3 plus 2. So that ends up being 3 to the negative 1 power. That is 1/3. Now, if you get the decimal for that, it's 0.3 repeating. You're not going to want to put that in Connect because you're going to have to round. So I would just keep it at 1/3 and then you'll be okay. And then maybe pick, I don't know, a bigger number, maybe pick 0. So if I do y equals 3 to the 0 plus 2, I get y to the 3 squared, which is 9. And so that gives you 3 points there to plot. Okay, so just erase this real quick so I have some room to do a quick sketch. And so I'll make my coordinate grid. And so we've got negative 2, 1, negative 3 is 1/3, and 0 is 9. Okay, and so you can see I have an exponential growth shaped graph, which looks good. And then again, you can always check Desmos to make sure that your graph is correct. And then let me just show you real quick what this looks like on Connect. So on Connect, here's an example that's very similar to the one I just did, and it's asking us to graph this. An easy way to do this is to click on plot the point, and so you can just type in the point you want it to graph. And so just like this last example, what we could do is find, you'd figure out how to make this exponent 0. Okay, well, this exponent is 0 if x is negative 2. And so if x is negative 2, then if you plug that in, you end up getting 2 to the 0 power, or 1. So I can just type in negative 2 and then 1. And then I could plot the point. And so you'll do that a couple of different times. And then once you plot, I would say 3 or 4 points, then you can click on this button over here, which will connect the points and make a graph. Okay, so let's look at another example. So this is another graphing example. We have y equals 3 to the x minus 1. We want to know, is it exponential growth or decay, and then create a sketch. So we first want to look at the b value. So remember, the general form of exponential function is f of x equals a times b to the x power. So we want to look at the b and decide, is it greater than 1 or less than 1? So this is greater than 1. So it's greater than 1. So it's exponential growth. Okay, so we're looking for a graph that looks, like this. And so let's create a sketch. So the first thing we're going to do is we're going to look at our exponent. So our exponent is x minus 1, and we're going to figure out when is x minus 1 equal to 0, because when you raise anything to the 0 power, you end up getting 1. So it's just a really nice point to start with. So if we solve this equation or just kind of think about it, we can see that x minus 1 is 0 and x is negative 1. So negative 1 is a good number to plug in for x. So that's the first thing we're going to do. We're going to do y equals 3 to the negative 1. Oh, why did I say negative 1? That's not right. It should be positive 1. I was going to say that ends up not working out. See, I would have found my mistake because by plugging in negative 1, I wouldn't have gotten 0 there. So when we solve that equation, we get positive 1. There we go. And so if we do 3 to the 1 minus 1 power, then that ends up being 3 to the 0 power, which equals 1. Okay, so if we plug in negative 1, we're going to change that to, we change that to positive 1. If we plug positive 1 in for x, then we end up getting 1 for y. So we have a point 1, 1 on our graph. And then the next point, well, it's really, it's always up to you. There's no, rule here of what to do other than, to pick a couple points. And if you don't get nice numbers, you can keep picking some more. So I'm just going to pick 2 and 3. So I'm going to plug those in. So y equals 3 times, I'm going to plug 2 in, 2 minus 1. So that's 3 to the first power. So that gives me 3. And then if I plug 3 in, and you can tell just by looking at the equation that if I plug 2 and 3 in, that those are going to give me nice exponents, and I'm going to get some nice answers. So I get 9 there. So now I'm going to plot those points. So I'm going to plot, these are all just coordinate pairs or ordered pairs. So I'm going to plot 2, 3, and I'm going to plot 3, 9. Okay. If you wanted to plug in something like, maybe a negative 1, you could, but you don't have to. So really it's just going to go this way. But again, if you were unsure of where it goes in this direction, then plug in a negative 1 just to see. So what happens if I plug in negative 1? I get y equals 3 to the negative 1 minus 1, which is 3 to the negative 2 power. That ends up being 1 over 3 squared, or 1/9. If you could always use your calculator though, 3 to the negative 2 power. It gives you, now this calculator happened to give me the fraction. Other types of calculators, they might convert that and write it as a decimal. So now that's repeating, but it just shows you that when you plug in negative 1, you're going to get a really tiny number. And so this is going to just kind of hug that x-axis there. And there's a sketch of our graph. Now in example 2, we're going to look at an investment of $4,500 that grows at a rate of 4% per year, compounded monthly. We're going to use the compound interest formula below to write the equation representing this investment, and then find what the value of the investment is after 3 decades. So we're kind of going back, in content and revisiting the compound interest formula, which is kind of fun. So our principal in this case is going to be $4,500. That's that initial investment. So remember, P just stands for that initial investment. R is rate as a decimal. So 4% is a decimal. We're going to take that decimal place and go 1, 2 spots to the left. So 4% is the same thing as 0.04 as a decimal. So 0.04. Now n is the compounded period, so how many times it gets compounded per year. So if it's compounded monthly, we're going to divide it by 12, and then 12 times t is going to be the time. So if we're looking for 3 decades, a decade is 10 years. So that's 3 times 10 years each. So that's 30 years total. So 12 times 30, okay? And so we're looking for the value of investment after 3 decades. So I just want to point out before we evaluate this with our calculator that whatever is inside here, the base of the exponent, this is kind of like our b, and that's the growth rate. Okay, and so all we have to do is evaluate this with our calculator and we can find the value of the investment. So I'm going to do 4,500 times 1 plus, now if you have a fraction button, you can use it, or you can just do 0.04 divided by 12. Either one will work. raised to the, you can multiply those ahead of time and write them on your paper, or you could do what I'm doing and just punch it right in all at once. And so you end up getting a value of $14,910. And since this is money, I'm going to round to 2 decimal places, so 74 cents. So if someone invests $4,500 with these terms, they're going to end up getting $14,910.74 after 3 decades. So long time in the bank, but that's, quite a bit of growth. Okay, so last example for exponentials. Riverside County, California is one of the 5 fastest growing counties in the US. One estimate uses the function f of t equals a sub 0 times 1.04 to the t to model the population. So a sub 0 is the population at time t equals 0, so kind of like when, it starts, and t is time in decades. So be really careful when you're reading to acknowledge when they say things like decades, because sometimes that will throw people for a loop. The population in 2007 reached 2 million for the first time. Use the model to predict the population in 2027. Okay, so I'm going to write down my function. Okay, we were told a sub 0 is the population at time 0. Okay, so we need a population, and the only population that we were given was that 2 million. So if we say that at t equals 0, the population is 2 million, that's just basically saying like, hey, when we start the clock or the counter, we'll just think of 2007 as sort of where we start, and we'll think of 2 million as the population at that time. So what we're going to do is we're going to rewrite this function with 2 million in for the initial population. And remember, t is in decades, okay, which are 10-year chunks. So if we want to know what is the population in 2027, then we have to ask ourselves, how many decades is that compared to, how many decades have gone by comparing that to 2007? So actually, you know what, I'm going to write 2007 first. So if we go from 2007, which is sort of where we start, with that population of 2 million, to 2027, okay, that's 20 years, okay, which is the same thing as 2 decades. So basically what we need to do is we need to put a 2 in for that t. And if we do that, that'll give us our answer. So we're just going to find f of 2. So we're going to take 2 million times 1.04 to the second power. I'm just going to count my zeros real quick. So easy to put in a 0 or miss a 0, and it really throws off your answer. And then we just hit calculate. So we end up getting a population of 2,163,200. And it never hurts to just double check, like, we've got our equation and our b value is positive, or not positive, but it's bigger than 1. And so we should have an exponential growth situation. And so we want to make sure, 20 years later that our population grew, and in fact it did grow. So it started at 2 million in 2007, and then it grew to 2,163,200 in 2027.